Hey everyone, welcome to my channel Redirect AI. This is me Sachin, and today I'm going to talk about dimensionality reduction techniques and why do we need dimensionality reduction and why is it important? What are the available techniques in machine learning for dimensionality reduction, which you can use for a you can use on a widespread scale for different use cases. So as you can see on the screen right now, we have PCA, LDA, kernel PCA, when to use which technique, why to use one technique over another, and why not use one technique over another, and why not use one technique at all. And we'll also see the Pythonic implementation of it. So ideally, coming to why do we need this dimensionality reduction, right? So one very common answer is that it makes your model very complex actually, and the model tends to overfit. Model is never able to understand on the numerous features, no matter what X model you bring into action, and no model is going to understand the fit the features really well. So somehow to handle the overfitting, we say this that we need dimensionality reduction, and this is where people say it's said actually, it's not people say, it's said actually that it's a curse of dimensionality as well. So yes, the curse makes your model go haywire, you can say. It overfits, or yeah. But ideally, it's very common to have access of thousands of features, or or maybe hundred of thousands of features, and not all of them are useful, and will practically never be able to collect enough observations for any use case, and thus we have never enough data for our learning algorithms to predict correctly. Now, at one point I'm saying we have thousands of features, not all of them are useful. At another stage I'm saying we're never going to have enough data. So what I'm trying to say, right? Yeah, that's the curse of dimensionality. It's not always the more you have it's better. No, it's not always like this. See, so the goal of dimensionality reduction is either to extract new features of basis the available data set, or select the available features. So it can be divided into two parts. One is feature extraction, where these techniques come into action, like PCA, LDA, kernel PCA, and many more. One is feature selection. Feature selection, one example you must have seen in random forest, we have feature importance. We can select the important feature there. One is we can select the features using the statistical techniques like basis the variance, or many statistical tests like ANOVA, chi-square, etc. So ideally, goal of feature extraction is to reduce the dimensionality and transform our set of features so that the new features that we have is it's less than the original features, while still keeping the underlying information intact. And that is what PCA does as well. Putting it another way, we reduce the number of features with only a small loss in our data's ability to generate high quality predictions. Getting my point? So whenever we reduce the data, there's still a data loss, but we try to minimize it. We can say that the components, the principal components, or the reduced dimensionality that we have created or projected on another plane retains around 99.99% of the data. So that is what that is something that we bank upon. Now, only one drawback is the new features are not interpretable by humans and will just appear as a series of random numbers. So that's why it's complex to explain as well to maybe your clients, or maybe for yourself to understand it first, then later on you can explain it to your clients if you can. So the first technique that we'll look at is PCA. PCA is again principal component analysis, and it's a very popular linear dimensionality reduction technique. See, PCA, projects observations, onto a principal components of the feature matrix that retain the most variance. So what are these principal components? We'll just have a look. So now, since it projects the data, basis no assumption on another principal components or a vector, you can say, That's why it's a unsupervised technique. Unlike LDA, which is a supervised technique, we'll just see in the tutorial. Thus, PCA is a unsupervised technique, meaning it does not use the information from the target vector and instead only considers the feature matrix. So that's a very important point to remember. Now, for a mathematical description of how PCA works, I'll just mention some external resources, and maybe I'll try to explain some bit of mathematics as well, if I'm able to. And then maybe basis that mathematics, you will get some intuition behind PCA using a simple example. So now in the coming screen, we'll have a figure. In the figure, we're going to have two axes. And just let's have a look at the visualization now. So see this first figure A, we have some data points on. Let's say we have two features only, x-axis and y-axis. And on the figure B, you see the axes have been changed. So, and it says center. So, PCA centralizes the data first. It will bring the data to the center and it takes this assumption that data has a center. So that's another crucial point about PCA, that it assumes that data has a center as well. Now, third thing, what it'll do is, it will just do like a regression. As you can see, we have a red line and a red X. So basically, it will try to fit a best fit line. As you must have seen in regression, ordinary least squares. That is what PCA also does. It creates a best fit line and tries to project those points onto a new vector or a new line whom we call principal component. As you can see in the figure D, that the green line has the projections, and now these projections where these points, these dotted lines are cutting the green line, becomes the representation of the actual data. So it takes two major assumptions, that it centers the data and it fits a line. Now finally, what's its the loss function, or you can say the cost function maybe. I've already explained in a separate tutorial what a loss function or what a cost function is. So ideally here our cost function is x. It tries to reduce the x. Now why x? We already have a projection to this from our point to the green line. We already have a projection, but why does it want to reduce x? So yeah, I've prepared some notes for it. So let's assume you have this data where you have two features, G1 and G2. As you can see, the green dots are the actual points, the red one is the principal component, and we'll try to find a line that minimize these projections. All right, but as I said, that we'll try to minimize the x. Now we'll just see where this x is. In the figure below, you see that I have created a triangle like A, B, and C, where A happens to be the hypotenuse and B and C happens to be the other sides of the triangle. So ideally, we have this relationship, A square is equal to B square plus C square. Now, this A is fixed, okay? Whether we centralize the data or we do anything, the relationship between other points is going to remain the same. So that's why the distance from origin is going to remain the same. Actually, the relative distance from origin is going to remain the same. Thus, we are left with B and C. Now, if I say that, if B gets bigger, then I think we don't have a best fit line because our projections are very far actually. And our cost function is to reduce B. All right. We try to find a line that reduces B. If we say that we want to reduce B, then I would say, that we try to find a line that maximizes C. Or vice versa, that I've written is if B gets bigger, then C must get smaller to keep a constant, and vice versa. So vice versa case that we look upon is reduce B and maximize C. And why C? Because computation of C is cheaper. That's why we maximize C and B gets reduced automatically. Now what is this? B is just simply we put it as sum of squared error, just like regression. Square because it tends to get positive values and we are interested in distance metric and not its magnitude, not its orientation or polarity, you can say. And the best fit line found would be our first principal component. Now see, PCA in scikit-learn is implemented using PCA method, and before going to that, see, this is about the first principal component. Now, going to the second principal component. See, the second principal component would be nothing but it would be a line perpendicular to first principal component. And for this same line, we'll again calculate, this A, B, and C relationship. And this will again have some distances B, and we'll have a square of it, whom we call sum of squared error. And thereon, we'll get two more terms. One is eigenvector and one is eigenvalues. So this vector C is actually called the eigenvector, and the sum of squared of all the B's, for a particular principal component will be called as eigenvalues. So all the principal components, principal component 1 will have some eigenvectors and it will have some eigenvalues, again for component second and the component third. And why this is important? Because mathematically it will help you understand the explained variance that this principal component has. Now PCA is implemented in scikit-learn using the PCA method. And it has certain parameters like n components, which has two operations, like depending upon the argument provided. If the argument is greater than 1, n components will try to return that many features if it's an integer, and if it is more than if it is less than 1, it will be taken as a kind of a variance parameter between 0 to 1, 1 being 100%, 0 being 0. So it is common to use values of 0.95 or 0.99 because we want variance to be explained in a maximized manner. All right. Apart from it, we have another parameter called Witten, which transforms the value of each principal component so that they have zero mean and unit variance. These are some statistical terms, but need not worry about it. It's fine. Another parameter and argument is SVD solver, which ideally we keep it, we try to keep it as randomized. SVD solver randomized, implements a stochastic algorithm to find the first principal components and often significantly less time. Since we are computing C, which is, the cost of computation is very less, but it still takes a toll, if you have very large dimensional data space. So yeah, let's implement it and see how it goes. Alright, so I'll just load the standard scalar first from pre-processing for the Z transformation because we want feature on the same scale. And now I'll just call the PCA from the decomposition, which holds the functionality for PCA. And finally, I'll call the dataset as well. Now let me just run it and no module. Oh, oops, I made a mistake. Yeah, let me just run it again. All right then. Now we're using the digits dataset today because it has very high dimensionality. Just a second, load digits, and we'll use the feature return xy true. It will unpack into features and target. Yep, that's right. So you have features. You see, you have 64 columns and 1797 rows. I'll just apply the PCA and I'll initialize it. You see, we have the same components, parameters that we discussed. We can also, access the documentation. Let me show you just a second. So if you don't have the documentation handy from scikit-learn, you can go to the internal downloaded documentation and like a multi-line comment. So we have like number of components. If it's between 0 to 1, it will be the variance, the amount of variance that needs to be explained. If it's more than 1, that will be number of components. We'll try both. I'll just keep it at 99. It means 99%. Witten equal to true, so it's another hyperparameter. We'll just again have a look again. So it's basically scales the components so that we have unit component wise variance, like unit variance, I would say. All right, let me run it. So PC has ran and we've got one component and it has multiple features just like this. I'm just checking and taking a walk around so you can just replicate the same to get an idea of how it works. So we'll just transform the features, fit transform, and we'll just pass on the only features, no target, because it's an unsupervised technique. So we've got 41 features now, reduced by 23. And so earlier it was like this, now it's like random numbers. As I said, positive, negative, real numbers are very difficult to explain, but yeah, it works. Now we'll just have a look at the explain variance now, accessible by the attribute explained variance. So yeah, it gives the explained variance of all the 41 components. We can call it in a separate data frame. If you want, you can check the dimensions as well. So yeah, it has got 41 dimensions. Now again, these are random numbers and the magnitude of variance is there. So how to understand how much of variance is being explained by individual components? We can just use the explained variance ratio parameter for that, which we can access by PCA explained variance ratio underscore, and we'll just run it. Yeah, we got it. So if we'll just sum it up, it will come out about 0.99. So this is like 0.14 means 15%, and so on and so forth. Now let's try one more thing. Let's limit the number of components to 5, and let's see how much variance do we get. Is it able to capture in 5 components? Let's have a look. We've got 5 dimensions. Yep, these are the 5 components, and the variance ratio is already there. Yeah, right. So no, we're not able to capture maximum variance in 5 components. So machine decided that at least we should have 41 components for it. So we'll see in a separate video how do we decide on how many components do we need. So we can make a code that once we have reached certain threshold of variance, stop at the number of components. So yeah, with 10 as well, it hasn't increased much, so no worries, we'll see in a separate video. I just wanted to show you how PCA works. Let's move on to another technique now. See, PCA is able to reduce the dimensionality of our feature matrix, that is the number of features. And standard PCA uses linear projection to reduce the features we just saw. But what if data is linearly inseparable? What do you do about it? See, when data is linearly separable, we just draw a straight line or a hyperplane between different classes and PCA works well. But what if our data is not linearly separable? Example is that you can only separate classes using a curved decision boundary. So that is what I meant from linearly inseparable data. Thus, the linear transformation will not work. And what do we do about it? So in this case, we'll go with kernel PCA. So kernel PCA, when data is not linear, it's fine. We can go with the kernel PCA. As you can see in the figure that when data is not linear, principal component will mix 2 classes. And when we have kernel PCA, it can separate the classes because it can use a feature called, it has the functionality to implement the spherical boundaries. So that's how it is able to separate both the classes, and it's a better technique over PCA if you have linearly inseparable data. So yeah, let's implement it and discuss further there. So now our data is not linearly separable. So in our solution, we'll use scikit-learn's make circles dataset to generate a simulated dataset, and I'll call PCA and kernel PCA from decomposition. Yeah, so make circle makes the data linearly inseparable. All right. Just a second. Yep. All right. That's fine. We've got the libraries in place. I'll just call the features, and so this is for the underscore is for the another values that get unpacked. I'll just call how many samples we need, the random state, how much noise do we if you want to introduce or not, and I'll add the factor as well as 0.1. You can read more about it if you want through the internal documentation, just like this, and you can read about how what is this noise, what is this factor, and what is this make circle dataset. All right, I'll just run it. We've got the features with 100 rows and 2 columns. All right, as the next step, I'll call the kernel PCA and I'll add the kernel as RBF. See, in SVM video, I have introduced it. What is kernel? So downside of kernel PCA is we don't have option to set percentage variance to be retained. Instead, we have other set number of hyperparameters in kernel PCA, which they come with own set of values like gamma, radial basis, etc. So that's how it goes on. That is just one downside, but through trial and error and grid search we can find the best possible values. So for now I'll just add I want one component out of it, and let's see, we'll just fit transforms. It's also an unsupervised technique. We'll just pass on the features through it. All right, now let's have a look. All right, we got the features reduced to 2 now. Earlier we had what? Just a second, I think I opened the wrong window. Okay, yeah, features got reduced from 2 to 1. Let me check the explain variance ratio here as well. And yeah, it doesn't have. Okay, so it doesn't have the explain variance ratio. No worries, you can check it on the scikit-learn documentation as well. What other attributes it has, and even try. So yeah, this is how we did KPCA, and let's move on to the another technique called LDA. All right, so we saw how we implement PCA and kernel PCA, and let's move ahead with the next technique called LDA. So linear discriminant analysis. It is a technique of reducing features by maximizing class separability problem. Okay, so we'll try to separate out the class, the difference between two classes, and also that you want to reduce the features to be used by a classifier. So when we have a classifier algorithm at hand, maybe we have a categorical target variable, we go with the linear discriminant analysis and we try to maximize class separability. So LDA is a classification that is also a popular technique for dimensionality reduction. LDA works similarly to principal component analysis. In one case, that it projects our feature, it projects our how do I say it projects our feature space onto a lower dimensional space. And in PCA, we're only interested in the component axis that maximize the variance in the data, as we saw. But in LDA, we have the additional goal of maximizing the difference between two classes. Now, in this example that you see that we have class 1 and class 2, we have, on x-axis, x1 dimension, we have class 1 and class 2, and in x2, we have both the classes together. Now, in this example, let's say we have 2 target classes and we have 2 features. Now, if you project the data onto the y-axis, on the x2 axis, the 2 classes are not easily separable, right? Because they overlap. But while if we project the data onto the x-axis, we are left with a feature vector. Definitely, they are easily separable. Thus, we reduce our dimensionality by 1. And that still preserves class separability. Now, in real world, of course, the relationship between the classes will be more complex as usual, and the dimensionality will be higher, but the concept remains the same. Okay, so let's implement this as well and see how it goes. We can use the LDA for classification as well. I've explained that in a separate tutorial, that how we can use LDA classifier for a classification problem as well. Yeah, let's implement it and see how it goes. In scikit-learn, LDA is implemented using linear discriminant analysis, which includes some parameters like n components, which indicates the number of features we want, and we have the attributes like explain variance ratio, which tells the variance explained by each output. So let me just call on the important libraries once again, and we'll unpack features and target from the datasets of. So we'll use the iris here, since LDA is used when data is going to be ingested by a classification algorithm. All right. And just remove some of the redundant values. We don't want that. We don't want it. Okay, we are good. Neat. All right. So I'll just call LDA and we'll just see what components it has. All right, looks very much similar. The n components, that how many components do we need? All right, I'll just fit it. So right now, while fitting it, we'll pass on the features as well as target, and then we'll transform the features. So it's a supervised technique where we learn the target classes as well. So while fitting, we'll pass both x and y, and to transform x, we will pass both features and target. All right, again some confusion, positive, negative, real numbers, but don't worry about it. We'll run one more. Just a second, I want to show you something. Whether do you have to fit and transform? So yeah, how it says that, okay, I'm missing one argument. You see, it's pretty much the same. So you can just directly use the fit and transform. Yeah, that pretty much solves the doubt as well. All right, let's see if it has explain variance. Oh, okay, it doesn't have the explain variance. All right. I was under impression that it has explained variance. It should have explained variance as well if it's able to explain the ratio. Okay, no worries, no worries. I'm just checking the implementation. How to decide upon how many idle components are required. So that is something we discussed, that we will prepare a code and we can run LDA with n components set to a none initially to return the ratio of variance explained by every component feature, and then we'll calculate how many just it gets too difficult while you're narrating and writing the code as well. Hold on, you'll just see in a moment what I'm trying to explain. So we're making the function to stop the LDA once we have reached certain variance. All right. Okay, when you set the components to none, you see it has taken the automatically how many components that would be required, that is 2. All right, so for two components, we've got the ratios as well. You can see on the console like 9 to 9 and 0.08%. All right, now let me create a function selecting components. We'll pass in a ratio. What is our goal variance? It should be a float, but it can take values int as well. All right, and then we'll set initial variance explained so far as total variance to 0, and then we will set number of components initially to 0. Now for explain variance in variance ratio, new total variance would be sum of the explain variance added with the total variance. So we'll just add plus equal to, and yep. Now once we proceed, we have to increase the number of components by 1. I'm going a bit slow here because it's a really important function. Now what happens if we reach our goal, right? If total variance is more than or equal to our goal variance, what we'll do is we'll just I think we're good to go there, and we'll just break our loop, and we can print goal variance reached, and we'll just hit break. All right, and we'll just return and components. Okay, it's going some error. I don't get it. What's wrong here? What's the issue? Break outside loop? No, it's inside the loop. What's wrong? Sometimes these issues pop up during runtime as well, and I'm sorry I'm not able to remove it from our tutorial. What happened? Just bear with me for a moment, please. So these are like runtime errors that you'll face as well. So yeah, I think it's a good learning as well. No, I'll just put it back. Oh, Okay. Oh, sorry. So the if is out of loop actually. Yeah. Yeah. So, all right. We got a function and let's run it. Okay, I'll just call it, selecting components, I'll pass in the var ratio and threshold at 0.95. I think it should stop after one. Oh yeah, it stopped after one because we had two components only. Yeah, I think we had two components. So yeah, this is how, we apply LDA and yeah. All right, everyone. Thank you. So today we discussed some of the very important techniques like dimensionality reduction, by feature extraction, in which we saw PCA, kernel PCA, LDA, and what are eigenvectors and eigenvalues. Now, discussing about why not. I'll just try to put it in a very simple manner as I can. This is my experience. See, one key criticism of PCA is that the transformation is fairly complex and the results are therefore hard to interpret, as we saw in the code as well. The principal components and the projected vectors are real valued and they are real values, so they could be positive or negative as we saw. Now, the principal components are essentially linear combinations of rows which have been centered, and the projection values are also linear combination of the columns. Now, in a stock returns application, for instance, each vector is a linear combination of time slices of stock returns. Definitely. Now, what does that mean? I mean, you have some negative values, you have some positive values, and it's really hard to express a human understandable reason for the learned factors. Therefore, it is hard for analysts to trust the results. Now, if you can't explain, why you should be putting billions of others people money into particular stocks, you probably won't, choose. You probably won't choose to, use that model. Makes sense to me. I hope it makes sense to you as well. I'm able to explain why not PCA. But yeah, it's a key criticism actually. But ideally, we end up, building financial index using PCA. Lastly, it is not, best not to apply PCA to row counts. Like, if you have like word counts or you have in natural language processing, you have, sparse matrix like that. But that doesn't mean that you should not apply it. It's a very helpful feature I have implemented in many of my projects, and it really helps out to reduce the number of features, still retaining the information, and you make a good, better, less complex, less overfitted model, and it serves the purpose. It serves the purpose when you don't have much. Much vested interest in what these features are, because in some projects client may agree to you that okay, it's fine if I am not going to understand few of the features, that's fine, but tell me how my model works, how the precision is, how the recall is, how close is the regressed value. So this is the reason that such counts often, and also it is sometimes affected by large outliers, so it is it's very much sensitive to high outliers, so it's always advisable to scale your data. And what else I can say about it? So yeah, it's a good idea to try dimensionality reduction techniques after watching this tutorial. So yeah, let me know what your thoughts are. Please leave them out, your feedback in the comment. Your feedback would be really constructive, and please do like, subscribe, and if you face any more challenge, you can reach out to me on my personal email ID, and I will see you in the next one.